Our next speaker is Partsvania with the talk and the name of this talk. Yes, here it is. On one non-local problem for second-order linear singular differential equations. You are welcome.
Thank you, dear Irina, very much. So, good afternoon, everyone. I'm happy to see you here, my dear colleagues. Everyone, I won't count them. So, and this is the first time I'm participating in a conference, Petrovsky conference, and it's honor for me, you know. And thank you, my very dear Irina Viktorovna, for this chance. And I hope that next time I will participate not online, but I will come to Moscow and will participate like face by face. Thank you once more, everyone. So this talk I will discuss in English, Ирина, потому что там много этих дней. Хорошо? Нормально? Okay, I will give my talk in English. Okay. Well, as already Irina Viktorovna mentioned, my talk concerns the one non-local problem for second-order linear singular differential equations. Mainly, we consider the, just one moment. Yeah, okay. Today, in my talk, I will give results which are new and unimprovable in a certain sense for the unique solvability of so-called Dirichlet type problems for singular second-order linear differential equations. On the open interval, we consider the equation u double prime equals p1 t u plus p2 t u prime plus qt. Let's call it equation 1. And we consider this equation under the following non-local boundary conditions. So from A to A0, u t d p1t equals c1, and from b0 to b ut d phi2t equals c2. Okay, these are conditions 2. And here we assume that P1 and P2 as well as Q, they are defined on the open interval AB, and they are measurable functions such that the integral from A to B, T minus A, B minus T, P1, absolute value of P1 function plus the absolute value of P2 function. This integral is convergent. And the integral from A to B, again with the weight of T minus 1, B minus T of Qt, is also convergent. Okay, here A0, B0 are numbers between A and B. Yeah, C1, C2 both are real numbers. As for the functions phi1 and phi2, so they are defined in different, just one moment, I want to take this eraser. Yeah, P1 is defined on A0 to R, and P2 is the, let's call it 3 because later, so all theorems and corollaries are formulated under the assumption that the condition 3 are fulfilled everywhere. Okay, Phi2 is from B0 and B, and they are such functions that they are non-decreasing functions, Phi1 and Phi2, and satisfy the conditions. Phi1 at A0 is strictly greater than Phi1 at A, and Phi B is strictly greater than P2 at the B0. Okay, and so this is condition number 4. So we assume that these conditions are satisfied everywhere. Okay, number 3 and number 4. Okay, so now look at these conditions 3. These conditions guarantee that every solution of this equation, every solution has one-sided, corresponding one-sided limits at the points A and B. And so we assume that the values at A and points A and B of that function are these right and left hand limits. So in these conditions, it is assumed that U at A, this is the right hand limit of U, and similarly, U at B is assumed to be the left limit of U. Well, now, as the T, sorry here, T approaches B from the left. Okay, so the conditions too, particular cases of this are Dirichlet boundary conditions. And I will write here this. U at A is C1 and U at B is C2. Let's call it 2 or 1 prime Dirichlet conditions. And that's why we call the problem 1, 2 Dirichlet type non-local boundary problem. Okay, now, so I will now maybe show the theorem, but before I want to tell you that we are mainly interested in the case when functions P, 1 and Q have non-integrable singularities at the points A and B, but however, the results below are new also for the case when these functions, these coefficients, are integrable on AB as well. Okay, and I want to mention one more thing here, that the requirement on the functions P1 and Q here and here to be integrable with the weight AT minus AB minus T, both, it's essential and it cannot be weakened. Indeed, if we assume that P2 and Q are integrable on AB, but P1 is of constant sign, then for the solvability of problem 1, 2, it's necessary that the integral T minus 1 A B minus T P1 T dt is convergent. And in a similar way, also the same with Q. Okay, now in order to formulate our theorems, so we need to introduce some notation, and maybe I will write this also here because maybe sometimes I will need to refer to this. Okay. So H for any continuously differentiable function omega W, okay? So we introduce the function H1, which is to be P1, depends on P1, P2, and omega. And it's the negative part of P1, then plus the negative, times W, WT, plus the negative part, and the negative part of P2 times W prime T. As for H of H2, P1, P2, and omega, that's the negative part of T minus with WT minus positive part of T and W prime. Okay, so, and we formulate our main theorem using these notations. Namely, the following theorem, the main theorem is here. And now I will show this. Okay, just one moment. This one. Okay, if there exists such a number T0 and continuously differentiable functions W1 and W2 defined respectively on A T0 and T0B, and both are positive, you see, such that conditions 5.1, 5.2, and 6 are satisfied, then our problem is uniquely solvable, the problem 1, 2. So here you see W at 0 at A is 0, at here W at B is 0, derivative is positive, here negative, and the integral condition is here 5.1 and 5.2 are formulated in the sense of in the language of H1 and H2. Okay, and this is also important. Now I will give example that shows that the condition 6 here is unimprovable. It cannot be changed by equal to. Okay, so next is example, and let's construct P1 to be in that equation such that from A to T0 it's minus R1 and function R1, and from T0 to B minus R2, where the functions R1 and R2 are defined by these equalities. Okay, as for W1 and W2, let's be this function defined like this. Pay attention that the W1 is this almost same this denominator of this, but in addition multiplied by T minus A. So P2, let's be identical to 0. That it's very easy to check that conditions 5.1 and 5.2 are satisfied. When substitute here, you will see that, and easily integrate, you will see that 5.1 and 5.2 are satisfied. But as for this 6, here we will have exactly 2. One, it's the limit, simple limit of this, and 1 here, exactly 2. But in this case, so we see now, if the functions P1 of W1 and W2 are like this, in this case, all the conditions of theorem 1 are satisfied, 5.1 and 5.2, but instead of 6, we have equality. But in this case, the homogeneous equation with homogeneous conditions have a non-trivial solution. It's easy to check that this function ut is a solution of this homogeneous problem. And since a homogeneous problem has a non-trivial solution, that it means that our non-homogeneous problem for any Q has either no solution or infinitely many solutions. Thus, we show that the condition 6 is unimprovable. Now, corollary 1 from the main theorem. Here we assume that so for any there exist such numbers T0, alpha, it's important to be greater than -2 and beta as well. As for L1 and L2, they are from the interval 0 and 1, and the condition 8 is satisfied. Also, P1 and P2 function satisfies these conditions. Okay. In this case, we have the unique solvability again for our problem. And if you apply the same example, it's easy to check that this condition is also unimprovable, and we can't write here equal to. Next corollary, so again, the unique solvability, and we have such a conditions 9 in this case. In this case, the problem is uniquely solvable. Here, this is also unimprovable conditions here, this one and that one, and it can be replaced by the equalities with 1 plus epsilon, no matter how small epsilon positive number is. And yeah, we can check this like if P1 is such that it's given by this as an example, if you remember here, yeah, if such P1 we have, and alpha and beta, they are greater than 1 over epsilon, and P2 is identically 0, then we can easily check that, conclude that the problem 1,0 non-homogeneous problem has a non-trivial solution, so we have no unique solvability for 1, 2, and thus conditions 9 are unimprovable. And the last corollary here is this. So if P1 and P2 are such that inequalities 10 are satisfied, and the constants L1 and L2 are such that sorry, that 11 is satisfied, then the problem is uniquely solvable. And here this 11 is unimprovable. We can't take this equal b minus a over 2. Indeed, you have, if you take p1 is identically negative L1, p2 is L2, and the sign of this, then we can check that the non-homogeneous problem has no solution, okay? Sorry, not no solution, but has a non-trivial solution, and that's we have no unique solvability of the problem. Well, and those corollaries we made, from there we have effective conditions for the Dirichlet, which are well-known, previous well-known results, and Dirichlet's non-local problems for that equation we consider, among them these multi-point problems. And the review of such results you can find in the work by Ivan Taryelovich-Kikuradze and Tariel Ivanovich-Kikuradze, appeared in Differential Equations in 2011. Okay, finally, I want to give the sketch of the proof of the main theorem, as well as to discuss some words about the non-oscillation of the homogeneous equation 1,0. Well, how to prove the theorem? So, according to the conditions 3 are here. Let's recall once more. Conditions 3, according to this condition, and 1,0, equation 1,0, I will rewrite once more which one is 1,0, because I will refer now it u plus p2 u prime, pt u prime. Let's call it 1,0, okay? So according to this condition, we can show that this problem 1, 2 is has a Fredholm property. That is, it is uniquely solvable if and only if the homogeneous problem here, if you take, I will write like this, 0, 0, and without this, homogeneous problem has only a trivial solution. Now, let's introduce the definition of the non-oscillation of the equation. We call the equation 1 this to be non-oscillatory if average non-trivial solution in the given interval has no more than 1, 0. Okay, so since phi1 and phi2, if you remember from the beginning, I mentioned that they are non-decreasing functions because of the monotonicity of these functions. Conditions 3 guarantee that the non-oscillation of this inequality implies that the problem, homogeneous problem 1,0, 2,0, has only a trivial solution. Now, we recently, with the Ivan Taryelovich, announced the College Day 2021, this December, we had this conference, and we announced the theorem about the non-oscillation under these conditions. And I will show this theorem now. Here, just one moment, here we are. Okay, this theorem that the conditions 5.1 and 5.2 in our main theorem, and also the 6 is necessary, is sufficient, and in the case when P1 is non-positive or P2 is 0, in this case also necessary for the equation 1,0 to be non-oscillatory. That's from this theorem. We have our main theorem proved. So I want to show this. Just one moment, please. Yes, here is this. It's published in our workshop this year. This theorem. Okay. Now about this that. From our corollaries, it follows the sufficient conditions for the non-oscillation, the well-known results. Among them are the results by Lyapunov, Hartmann, Wintner, and Vale-Poussin. So the first interesting condition for the non-oscillation of this equation was proposed by Lyapunov in 1896. Namely, he proved that if the integral, this condition is satisfied for P1 continuous function, and P2 is 0 there. Then the equation 1, 0, homogeneous equation is non-oscillatory. That is average. Its non-trivial solution has no more than 1, 0 in the given interval. 40 years later, the Van Kampen and Wittner showed that, constructed the example showing that this condition is unimprovable. Namely, if we add here plus epsilon, no matter how small epsilon is, then it's impossible to replace by this. Okay, then later also Hartmann and Wittner proved more general than this condition is. That I wanted to pass to that. Here is Van Kampen and Wittner's paper where the example is constructed showing the unimprovability of the Lyapunov's condition. As for the Hartmann and Wittner, they prove this general condition, okay? And so very often this theorem is said to be Lyapunov, Hartmann, and Wittner's theorem. Now let's formulate our corollary too. In the language of non-oscillation of the equation. If we take, instead of W1 and W2, respectively T minus 1 and B minus T, then these conditions are satisfied, then the equation 1, 0 is non-oscillatory. So, and from this corollary, it's easy to see that the Lyapunov-Hartmann's Wittner theorem is a consequence of our corollary, that is a generalization of that one. Also, let's formulate in the language of non-oscillation our corollary 3. Here we have these conditions 10 and 11. In this case, the equation is non-oscillatory, and the above corollary, in the case of this one, you have T0 and W1 is the solution of the initial problem like this. And if instead of 10 more strong inequality is satisfied, then from that theorem we have this one. I mean, in this case, we have the well-known result by Wallet-Poussin. So that's all I wanted to discuss. Thank you for your attention. Thank you.
Okay, thank you very much. It is wonderful talk, and thank you, Nino. And who have the questions? Who has the questions? Nino, I have one question.
Okay.
You please show your first problem. Your first problem.
You mean problem or theorem?
Yes, the first problem, only problem. The first equation, the next one.
Okay, you mean the equation, this one?
Yes, okay.
Okay.
And as far as I understand, earlier you studied the delayed differential equation, yes, and you found some conditions for the existence of solutions. And can you say a few words about the connection between these results and that?
No, I have not yet connected this with delayed differential equation, so I got only these results for these ordinary equations of second order, like this. Maybe it's interesting, but I have no idea about this for now. No,
Now we have no connection. Okay.
Okay.
And the next question is on the Sharp theorem. It is very interesting that the condition when some integral is less than 2, but 2 is impossible.
This one.
Yes. Would you show an example? It was very interesting.
Yes. Here is the example. Yes, you can easily check. Okay. So, first your question. What's your question, Irina?
My question is that it is very interesting, and you check that this function satisfies the condition that integral is equal to 2. And the statement of theorem is not true. Yes.
Yeah, exactly.
Yes. Okay.
Exactly. So it's very easy to check. If I will start now, it takes you time. It's just simple computation shows that the condition, both are satisfied. But here you will get, when substituting, taking into account that R1 is this one, W1 is almost this denominator, cancel each other. So you will see that this is, and then divide by this. You look, so you will see that because we have less or equal than W prime. Then if you divide this, you have exactly one number here. Here also, so it's 2. But if the function P1 and others are constructed like this, then it's evident that the homogeneous has a non-trivial solution. That's why we have contradiction with the theorem. Okay, one condition is violated here, the 6, number 6, and so we have true the theorem. That's it's unimprovable. It's evident.
Okay.
Okay.
Wonderful. Thank you very much.
Thank you.
Other questions? Maybe somebody in auditorium? Yes, of course.
Sasha.
Sasha.
Hello.
Does in your case non-oscillation also imply positivity or negativity of Green's function?
Yeah, but so you mean, so this next step is to construct such an examples, and so I'm going to study this problem about the Green's functions positivity. Yeah, it's connected with this, and this is the next step that we will do this. Okay.
Okay. Other questions?
No more questions.
If there are no questions, let's thank our speaker again. Nino, thank you very much. We are very glad to see you here. Thank you.
And me too. So thank you very much. Thank you.